So, buenos dias, camaradas. I'm Nikita Tarakanov. I'm going to talk, do you hear me? Yeah. Okay. Yeah. So, as you can see, the title of the talk is Direct Text, Direct Way to Windows Kernel, but in fact, this talk is not going to be about direct text itself. Rather, that it will be about security of kernel video drivers on Microsoft Windows. So, firstly, I will talk about Wddm Model, and then basically I will make a deep dive into this research. So, originally, video kernel drivers, they were kind of like complicated. There were a lot of functionality, and before Wddm, it was XDM. It was a lot of mess. So at some point, Microsoft decided to change the model to like Wddm, and they made like a lot of things by themselves, like scheduling and other stuff. So basically, there are a lot of things that DirectX does. For example, scheduling, virtualization of video memory, and etc. So also, DirectX is not only about kernel. Actually, it's some code in user mode and kernel. And in fact, it's if we talk about part of user mode drivers of like three major vendors like NVIDIA or ATI or Intel, drivers of user mode drivers, they inject themselves between like a layer of GDI and DirectX. So basically, in user mode, you operate with like abstraction level, like abstraction things like handles, resources, context, but they represent like really complicated structures in kernel. So this is how diagram, like this diagram shows how it looks like. So basically, on the top there is application that uses some like video functionality. So there are like different things. For example, Direct 3D runtime, OpenGL, and GDI32.dll. It's a last layer that performs actually system call. So, for example, when application tries to render some scene, it goes via Direct 3D in user mode, and user mode drivers, video user mode drivers, they like basically hijack execution flow. They basically install some function pointers. They do magic that specific to particular video card. And then it goes next to GDI32.dll, then it goes to kernel through dxg-kernel.sys, and then it goes to actual kernel mode driver. So the only talk that has been made so far in this area is talk that made Ilya Van Sprundel 1 year ago at Black Hat. So basically, if we talk about attack surface, there are just a bit of system calls that are exposed for user mode to attack kernel mode part of video drivers. And so, as you can see on the left, there are just 7 functions, right? But in fact, the most interesting are escape and render, because in fact others, there are not a lot of arguments, and if you take a look at what kind of arguments and what kind of functions is that, there is like not a lot of interesting and potential vulnerable code. Like for example, query adapter info, it's like usually it's just a simple code that gets some information about video card and returns it to userland. But system calls like escape, the arguments are like buffers and sizes of buffers. And we're gonna talk in a bit about p-private data. So talking about execution flow, how it goes like all the way from application, from direct 3D to kernel mode driver of video card. So first of all, you need to create device, like abstraction. So it goes from user land through direct 3D to user mode driver, because like PFN actually it's a function in user mode driver that does like specific processing for particular video card, and it performs system call. Oh, sorry. So then there is a system called DXGDDI create device. Then in kernel mode, device that is actually big structure created. Then we need to get a context. Then we need to create a resource that leads to allocation of some memory in kernel. And then wait a sec, it's like long. Then after that, we can basically talk with a video driver. By talking, I mean like performing escape function calls or like rendering something, etc. And after that, in kernel itself, between DXG kernel runtime and kernel mode driver, there are a lot of processing, but it is done only like in kernel, but between different components. Okay, sorry. Yep. So this diagram shows, like I will show you later code. This is like starting thing before fuzzing. So basically, you get adapter from handle, like basically from device context. Then you can get like display name, and you get handle. Then you create device. Then you create context, and then you can apply fuzzing through calling escape. So talking about how like arguments are passed from user mode to kernel, unfortunately for attackers, unfortunately for developers, DXG kernel does a lot of validation. So basically, all buffers are fetched and copied into kernel pool or kernel stack. So basically, it you're not gonna find time of check to time of use vulnerabilities. In fact, if you check database of security fixes by Microsoft, in DXG kernel itself, it was like so far, like around 3 vulnerabilities have been found, and as far as I can remember, it was just time of check to time of use vulnerability that leads to read of some arbitrary memory. So not arbitrary memory corruption, just like kernel ISLR bypass. So, but the thing is, the problem is that there is a p-private data that basically is buffer, and it's vendor specific, and DXG and code in DXG kernel cannot validate it because it doesn't know anything about this structure. So, talking about reverse engineering fuzzing of D3D KMT escape. Basically, escape function, it's, well, I call it basically IOCTL, but for video drivers. If you like open IDA and find this function that processes a buffer, you will see that it has like some structure. So first the word has to be like NVDA, so I think it's NVIDIA. Third word has to be 1, so there is some like header. So structure of this header is the following. So the first D word is magic D word. I will tell you about later. Then second D word, I don't know, it should be like 1. Then third D word, it's p private data size, and by like fuzzing NVIDIA was not like very straightforward, because when you send a buffer and in system call you set like, okay, this is a buffer, this is the size of buffer, but inside the buffer in this structure they like validate it again. And so when you like blindly fuzz, they will check that size of buffer and this value they don't match, and it will basically drop buffer and will not process anything. There is also fourth reward is escape action, and the most interesting is the escape function ID, which is basically IOCTL like value. And after that structure, it basically data, like basically buffer. So talking about this magic D word, I reverse engineered and I discovered that there are just a couple of them. So I believe it's they differ by functionality. So for example, NVIDIA-X, I believe it's NVIDIA DirectX, NVGL, it's NVIDIA OpenGL, and I don't have idea what is CP. Talking about this field, escape function ID, there are two major ranges from 1.0.0.0.0 to 1.0.0.0.1.22 in hex, and from 7 and, to 1.8.2. So if you calculate in decimal, it's around 800 IDs, right? So in fact, it's 800 functions. So it's pretty a lot, right? Talking about ATI, the structure is a bit different. First word has to be like all the time 80 in hex. Then second word it should be like 10,000 in hex or 10,002. Then it goes function ID and then data. And they code ranges in a different manner. So basically they iterate through second byte, not like they basically go by incrementing in 100 hex. And the thing is, like, if you check the size of ATI video kernel driver or NVIDIA, they are pretty huge. I can be wrong, but ATI it's about like 20 megabytes and NVIDIA it's about 15 megabytes. And these pictures, it's basically dispatchers of escape call. So basically there is a huge switch. You see that a lot of cases. So basically here you see like two major ranges, and these functions actually it's one and another. So it's a lot of code, and here on the right it's ATI. So all we know that complexity kills security, right? So before I made this research, I was like, okay, I'm gonna find some vulnerabilities. But yeah, but when I got first results, I was kind of shocked. I will show you later. So talking about like code, how to like start fuzzing. There is a structure in DirectX SDK called driver info. So to start fuzz, you have to initialize the structure. This structure contains a couple of fields like handle, like device context, and couple of handles like adapter, device, and context. So this code, like, I don't know, like maybe the problem that there is no like sample in internet, or not a lot of people wanted to fuzz video kernel drivers, but in fact there is no like sample of this code in internet. You will not find it on MSDN and Centra. So basically I managed to figure like how to how to initialize this structure and start fuzzing by reverse engineering user mode drivers of NVIDIA and ATI. So basically, firstly, you have to get device context. You basically can do it by standard API get DC from null. It means from desktop. Then you get adapter from device context. Then you create device, and then you create context. And at that time, the structure is initialized, and you can start fuzzing escape and other attack surfaces like rendering, for example. Yeah, The thing is that unfortunately I'm on Mac, and I need a laptop with NVIDIA OTI, or I have a video of like video demo. So basically I can copy and show you it right now, or like after the end of the talk. It's up to you. Well, we can make after, okay? So, talking about some interesting vulnerabilities that I discovered. For example, this shows like null pointer dereference, right? So this code is triggered by this ID. Unfortunately, on 64-bit operating system, it's not exploitable anymore because you cannot allocate address at 0. But on 32 bits before Windows 8, it's very easy exploitable. You just allocate your code there, and that's it. But the interesting thing about this vulnerability is stack trace. So as you can see, this is a call of from GDI escape. Here we go to kernel Win32K. It's just a trampoline to DXG kernel. Here's the DXG kernel, DXG escape, DDI escape, and as you can see, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So nesting is 11 layers. So it's just good example how video drivers are complicated and they are pretty insecure. Then another bug, as you can see, like from this output from debugger, it's some memory corruption, right? In fact, it's a pool corruption. Well, vulnerability itself, it's out of bounds. Basically, they don't check index and of some array, and they use it without any checking, and it leads to writing outside of pool buffer. But the interesting thing about this escape ID, so this function actually contains 2 stack-based buffer overflows and 1 pool overflow. Well, actually, out of bounds access. So here, stack trace. So this function, like where crash happens, and this stack trace, and as you can see, that stack is corrupted. So again, 1 function and 2 stack-based buffer overflows, 1 memory corruption, and in 2015. So it's pretty bad. Yeah, I'm not gonna reveal which vendor it is, so let's keep it anonymous, but there are 3 major, right? Intel, NVIDIA, ATI. So from this statistic, unfortunately for attacker, the most of vulnerabilities that I discovered, or you can discover still, I believe, it's just a null pointer dereference on read. So basically it's just useless blue screens, useless denial of service. But on the other hand, there are quite exploitable vulnerabilities like out of bounds of write and execution on at null address. But the thing is that these statistics clearly shows that there is no quality assurance in these companies. So basically they haven't made any fuzzing at all. So talking about recommendation for developers, well, they are same as for any kernel drivers. So basically, if you work with like function pointers, like any pointers, check it with probe for read, probe for write functions. Fetch and copy buffers to kernel to get rid of time of check to time of use vulnerabilities. So yeah, basically use abstraction like handles and Sentra. So, but this is escape that is kind of IOCTL, and it's like not very interesting that other things that you can discover in video kernel drivers. So, for example, command buffers that you can use via rendering. So basically, command buffer is a stream, like, and in this stream there are GPU instructions. And the thing is that basically it's a GPU assembly code that will be executed on GPU. Problem is that it's hard to research this area because there are a lot of chipsets of like various GPUs, like 3 vendors. Each vendor has different like generations. Plus to that, like as far as I know, code it's very strict. So basically, if it goes like one GPU assembly instruction, it has to be like followed by another. So like fuzzing is not very effective, and reverse engineering by hands, it's really very, very time consuming. And the thing is that it's very, very interesting vector because GPU instruction, they basically process a lot of things like managing allocations, like paging of video memory, context management, and even execution flow. So potentially you can find vulnerability like in hardware, in GPU, that leads to privilege escalation, for example. And privilege escalation not just from user mode to kernel, but for example from user mode to SMM. Because if you find some memory corruption in GPU, it can bypass some restrictions and write directly to SMM. So it's a very interesting thing. And yeah, and the thing is, talking about command buffers, it's not just Windows specific. It's for Linux, for OS X, for iOS, anywhere where GPU is, right? So this is an example that the vulnerability itself is quite boring. Basically, there was like some command that is privileged, but it was not set that it's privileged, and like user mode call basically can change any like memory. So it leads to very easy privilege escalation on Android. And yeah, I want to really thanks Rodrigo Axel Monroy, it's my ex-coworker, and Rodrigo Branco for making this talk happen. They put really, really a lot of effort. And so I'm gonna show you video demo. Wait a moment. Where's like some organizers? I need thumb drive to copy like to this laptop. Sorry? Okay. Give me this thumb drive. Yeah, so while copying, you can like ask me questions. Yep.
Did you try running this in virtualized environments to see how they respond to this interruption?
I have, because I was like working on NVIDIA ATI, but because VMware and others, they should be like some like legacy video card. So I remember that vulnerabilities in the video, like in virtualized video kernel have been found, yeah. In VirtualBox and VMware. Sorry? Again? Sorry. Yeah, the thing is that such vulnerabilities have been found, yeah.
Yeah, there was a talk while the Black Hat thing released video driver escape in virtualized systems.
You are talking about Cloudburst? Yeah. Okay. Yes, sorry that I was not sober that time. So basically, it's like fuzzer that goes like from just a loop that generates random data and invoke escape system call. And it's gonna blue screen eventually. Just a bit. Yeah, the thing is that after 0 nights in the end of November or in the beginning of December or for New Year's, if I will make it public, I mean like fuzzers and other stuff. So the problem is that, you know, even vulnerabilities are fixed, yeah. So basically. So the problem with video drivers that unfortunately not a lot of people update them, right? And like they're kind of slow. For example, I just got back from Buenos Aires and I had talked with a person. He told me that like around a couple of years ago, he also like been working with. He didn't tell me about exact vendor, but he told me that from the moment he sent information about vulnerability till the fix, it took 1 year. I sent all results to NVIDIA and ETI back in February, and I still like don't know like is it fixed or not, and I'm afraid that it's still unfixed. So that's it. Any questions? Yes, it's Intel integrated. Yes, it's just third vendor. Well, basically there are 3 major vendors, right? Intel, and right now the most laptops they go with integrated Intel GPU. But the thing is, the video driver of Intel is the same DirectX, it's same Wddm Model. So, yep. I haven't talked about Intel because I ex-employee, so I. So any questions? Okay, thank you. Obrigado.